Like we said before, this tutorial deals with weak bases. Unlike strong bases, weak bases, as have been alluded to before, do not ionize completely in water to produce hydroxide ions. They exist primarily as molecules. When weak bases dissolve in water, they undergo ionization to varying degrees. The degree to which each different base ionizes in water is represented by what is called its ionization constant, Kb. The larger the value of Kb, the greater is the degree of ionization of the base. Based on the values provided on the right, it can be inferred that base strength increases from bottom to top of the list given. According to this list provided here, we can see that urea is the weakest base and methylamine is the strongest one because this has the smallest Kb value and that one has the highest one. Ionization of weak bases. The ionization of ammonia will be used to represent how weak bases ionize in water. I want you to pay attention to a small difference that we make here compared to when we did the ionization equation for acids in water. In this case, we're using a water molecule to show how the ammonia molecule is acting as a base according to the Lowry-Bronsted theory. According to the Lowry-Bronsted theory, because the ammonia is accepting a proton from water, it is acting as a base. And of course, the water molecule there is acting as an acid. So when this happens, we end up with ammonium ions and hydroxide ions. So be reminded of that. Whenever you're doing the ionization equation for a base, you must include a water molecule there and show how the hydrogen ion from the water molecule goes on to the base. From this equation, we can now write the ionization constant expression for the base. See how water is not included in this expression because water, being a pure substance, does not change its concentration. This is the water we're talking about. So only these three entities you're going to see in the expression. You're going to see ammonium ions, hydroxyl ions, and the base. So that's what we have there. Product of ammonium ions and OH ions divided by the concentration of the base, which is ammonia. Next, we'll try to see how we can calculate the ionization constants for weak bases. We'll use this sample problem here to exemplify how that is done. So two things are provided for us here. You're given the concentration of the base, which is ammonia, and we are given its pH, which is 10.62. And we are asked to calculate the Kb for ammonia. To find the Kb, we need to find the equilibrium concentrations of ammonium ions, hydroxyl ions, and ammonia. How do we go about doing that? If we can find out what is the concentration of OH ions, we can know what is the concentration of the ammonium ions, because according to the mole ratios here, X moles of that is giving you X moles of that and X moles of that. So these two here are the same. What will lead us to this? The pH will lead us to calculating the concentration of OH ions, and I want to show you how that is done. We know pH. We can know what pOH is because, if you can recall, pH plus pOH is equal to 14. Therefore, pOH will be equal to 14 minus pH and is approximately equal to 3.38. So that's pOH. Now from pOH, we know how to calculate OH concentration. It's similar to how we calculate hydrogen ions concentration. OH ions concentration will be equal to 10 to the negative pOH, and pOH in this case is 3.38. So OH ions concentration will be equal to 10 raised to the exponent negative 3.38, and it turns out to be, in scientific notation, that, and in decimal form, this. Next thing we do is setting up our ICE table and insert every known quantity. Initially we have that concentration of ammonia and 0 of ammonium ions and hydroxide ions. We have just calculated this concentration of OH ions in the solution, which is identical to that amount there, and therefore an equivalent concentration of ammonium ions must have reacted to produce these quantities here That's why now we are removing that from its initial concentration, and it leaves us with that. So these here will be the final concentrations of all the entities. That for hydroxide ions, that for ammonium ions, and that for ammonia molecules. Put all of that into the Kb expression. We end up with the Kb for ammonia as being 1 times 8 to the negative 5. So this is the deal here. When they're asking you to find Kb, they'll give you the initial concentration, and they must give you something else such that in the end you can calculate OH ions concentration. In this case, they give you the pH. pH can give you POH, as we did here, and POH will eventually lead you to the OH ions concentration. Knowing OH, you can know that what that one is. We know these are produced. You subtract that from the initial concentration here, and you're left with all these concentrations at equilibrium, and you put those into the Kb expression, and that is how you find Kb. And this other question, we now want you to calculate the pH of a weak basic solution. In every case, they will have to give you the initial concentration of the base. Now they want you to calculate pH, then you must be provided with its Kb value, which is equal to this. This is the base. Then go ahead now and write the ionization equation for it. Like you said before, you must use a water molecule to show how the hydrogen ion from that is transferred onto this base here according to Lowry-Bronsted theory. So you end up with the acid and hydroxide ions. Again, write in the Kb expression what is not included in it. So it will be equal to the product of ethanoic acid times the concentration of the hydroxide there divided by the equilibrium concentration of what the base is. We can now set up our ICE table. In this case, we do not know what these concentrations are. We want to find these. But initially we have 0 and 0. So we're assuming that in the end, you're going to get a certain unknown quantity that is represented by X and X. And these must have come from an equivalent concentration of the base reactant, which is X. So we remove X from that. So in the end, you're going to end up with 0.100 minus X moles per liter. You're going to have X moles per liter here and X moles per liter. Insert these equilibrium concentrations into the Kb expression. So we're going to have X times X, these guys, over 0.10 minus X, that quantity there. And that is equal to Kb. So when we do the math, we end up with X squared over this 0.1 minus X is equal to 5.6 times 10 to the negative 10. To see if we can simplify our calculation, you want to see whether or not this expression here is approximately equal to the initial concentration. And to do that, we will take the initial concentration and divide it by the Kb for that base. And if it is greater than 100, then we can assume for now that this is approximately equal to 0.1. So if that is the case, we do not have to use a quadratic equation to solve for X. And you can see that this is much greater than 100. So we can assume that this is approximately equal to that. So we don't have to include this in the equation anymore. We can remove that. Now we have X squared over 0.100 is equal to the Kb here. X squared is equal to, that becomes negative 11 because we multiply by that 0.1 there, we take it across. The root of X squared will be equal to the root of this. It turns out to be approximately 7.4 times 10 to the negative 6 should be moles per liter. You know what X is? X is the concentration of hydroxide ions. But we are asked to find the pH of the solution. We don't have hydrogen ions concentration, we have OH ions concentration, which is this. So we can do a negative log of that to find its pOH, which turns out to be equal to 5.13. Of course, pH will be equal to 14 minus pOH, and it so happens that the pH is equal to 8.87. Why is it like that? It's a basic solution, therefore you expect its pH to be higher than 7. In problems like these, you're going to be given the initial concentration of the base and its Kb value. And you'll be asked to have either the pH or pOH. To find that, you have to go about to find the concentrations of the OH ions. Set up your IC table. We have 0 and 0 of these. Supposing that X moles per liter is being produced for each, then you have to remove that from the initial concentration. And when you do that, you end up with that as the final concentration in the equilibrium mixture. Put all of that into the Kb expression. See if this X is not very significant. To do that, take the concentration divided by the Kb. If it's greater than 100, then you can assume that these two are the same. But look, there's another thing I should have told you about. You have to see if your assumption is valid. You want to see if this assumption here is less than 5% of what the initial concentration is. Okay, so this is what we do. Take the initial concentration and subtract what X is. We're taking the initial concentration and we're subtracting that X there. We just found that. It turns out to be this. That's the difference. That's the difference it would have made. We want to see how big is this difference. So take its initial concentration minus that little difference there. It turns out to be this. Is this greater or less than 5% of the initial concentration? So you take it, divided by its initial concentration times 100%, and it turns out to be only 0.1%. So our assumption is valid. Okay? And this is what the pH of the solution is. Finally, we want to show you the relationship between Kb and Ka. So the acid that we will use to show the relationship between it and its conjugate base is ethanoic acid. So won't you look at ethanoic acid and the way it ionizes in water? Ethanoic acid ionizes in water to give you ethanoate ions and hydrogen ions. This is the acid, and this here is called its conjugate base. Writing the ionization expression for the acid, we have the concentration of ethanoate ions times that of hydrogen ions over the equilibrium concentration of the unionized ethanoic acid. This is the base. I want to right now show you how that is behaving like a base in water. Remember, when we write the ionic equation for the base in water, we must include a molecule of water to show how the proton gets transferred onto the base. And this is the equation here. The Kb for this base is written as the concentration of ethanoic acid times the concentration of the OH ions divided by the concentration of the ethanoate ions at equilibrium. So this is the Ka expression for the acid, and this is the Kb expression for its conjugate base. Let us see what happens when you multiply Kb times Ka. Expressions. Or Ka times Kb, same thing. This is Kb, and this is Ka. You can see that the ethanoate ion concentration here can cancel out the ethanoate ion concentration here. You can see the ethanoic acid concentration here can cancel out the ethanoic acid concentration here. All you're left now is this. Look, that Ka times Kb is equal to the concentration of hydrogen ions times the concentration of OH ions. So generally speaking, Ka times Kb is equal to the product of those two guys, and that is equal to Kw. So putting all of that together, we have that Ka times Kb is equal to Kw. If you knew what Kb was, and you want to know what Ka is, Ka will be equal to Kw divided by the Kb value provided. Same thing could have happened if you knew what Ka was, and you want to know Kb, you just bring down the Ka here, and that would help you calculate in a very simplistic way what the value of Kb was. Let us look at two examples. If it is required to find a Kb for the conjugate base for ethanoic acid at SATP, these things are all measured at SATP, okay? At different temperatures, they have different values. So the Ka is 1.8 times 10 to the negative 5. And you won't know what Kb is. Take Kw and divide by Ka. So that's Kw divided by the Ka provided. It turns out the Kb for the ethanoate base is this. Look at another one. If it is required to find the Ka for hydrocyanic acid HCN at SATP, knowing that its Kb is this, it can be done as follows. Ka will be equal to what Kw is, divided by what Kb is, that's Kw, and then what the Kb of the base is, and this is what the Ka of hydrocyanic acid will be. Well, thank you for that.